Ladies and gentlemen, today's class recording has started. So, yesterday we started in on applying the idea of conservation to energy. So we started yesterday talking about conservation in general. And we said that when something is conserved, the total amount remains the same. We may see some changes individually within the quantity itself, but the total quantity has to remain the same beginning to end. We said there were sort of two conditions that we had to fulfill in order to see conservation. What has to be true in order for us to see conservation?
Energy has to stay the same.
Well, that's what conservation is. When are we going to see that? And this is sort of true of any conservation. Say we have to have a closed system, right? Where we have nothing in or out. And when we talk about energy specifically, the total amount remains the same, but we have all these different kinds of energy that we have to account for. If we can account for all of these types of energy, not just kinetic and potential and gravitational and potential elastic, but heat and nuclear and chemical and all of those things put together, we will see the total amount remain the same. Okay? Under specific conditions, we will see a conservation of mechanical energy. What conditions have to be met in order for us to see a conservation of mechanical energy? Bella, go ahead. When there are only conservative forces acting on an object. And, like it says on the board, what are our two conservative forces that we look for? Gravity, and then springy, elasticy type things. Rubber bands, springs, trampolines, those kind of things. Okay? If those are the only forces acting on an object, we will see a conservation of mechanical energy. Right? What does mechanical energy consist of? Gravitational potential, elastic potential, and kinetic. The total of those three, right, has to remain constant. We talked about the idea that we may see individual shifts in one of those types of energy, but if one of these types of energy goes down, something else has to go up to keep the total the same. Okay? Good there? Right at the end of class yesterday, we were talking about this situation of the lady falling off the burning building, or the guy in the dress, whatever it might be, falling from this burning building, right? While we see her potential energy decreasing, her kinetic energy increasing, what are we seeing about the total here? Staying the same. Is mechanical energy conserved in this situation? Yes, right? It says so right on the board. Okay. So yes, mechanical energy is conserved in this case, right? As long as gravity is the only thing acting on her. All right? Good there? Okay. So I didn't get to tell you these two stories at the end of class yesterday, but they're good stories, so I wanted to tell you them. Well, they're not really stories, they're kind of more observations, right? So whenever I do this example in class, it always makes me think of two things. So first, this little like trampoline thing that firefighters have to catch people that jump out of buildings, nobody would do this today. Like today, you would pull the like extension ladder truck up next to the building, and you would put the little like canopy thing, not canopy. Right, there is definitely a danger here of them not doing this right and the person hitting the ground. But I wonder if, like, at fire stations across the country, if they have one of these things, like up in the attic, right? And every spring when they're cleaning, they're like, we got to throw this thing away. And one guy's like, no, no, no. What if the truck is broken and we have to, see, that's what he thinks. And everyone else just thinks that he's hanging on to a bunch of junk, you know, so. Maybe at the fireman's company picnic they do that. I don't know. So, okay. Well, so that's the other thing, that this picture always makes me think of the best day of elementary school gym class?
Where you used to.
When you walked into the gym and that parachute was out on the floor and you were like, yes. Okay? What? Come on. When we used to play that popcorn game, like where like, you know, everybody would shake it and you'd throw the Nerf balls in and they'd pop out and you had to catch them. Or when everybody like put it way up in the air and then you turn around and you made a big mushroom, you know, like, yeah, like, I mean, so, yeah. You got kicked out of gym one time?
Yeah, that was the day that we.
Bad boy.
It was the day that you did parachute?
Well, we did it a couple times, but this was 3rd grade.
It still scars him to this day. So,
I don't. Wait, you weren't a bird.
Have you ever seen, there's like
Yeah,
a line
I know.
of a bunch of little kids, and they have this blanket, and they throw it up, and then one of the kids just goes flying under, and gets like dragged under it.
no, I've not seen that.
And I
So- I've not.
kind of jumped in it.
So, oh well, it's really tempting. I mean, you know, so yeah, that sounds like an elementary school gym class thing to do. You know, so, but, all right. Before we move on to the next part, I wanted to finish up the outline that's on the front side of the outline. You'll see that next to the picture of the lady falling down the building, there is a graph, right? And so let's complete that graph together. Starting here, all right, so I'm going to draw me an x-axis here, and then I'm going to draw me a y-axis here. You guys have it already, okay? All right, so what is your x-axis labeled as? Time, okay? And so we'll go here with time. And then your y-axis, although not labeled, it has a couple of numbers on it, right? It has 5,000 and 10,000, but what unit are the 5,000 and the 10,000 in? Joules, meaning that what's on our y-axis? Energy is on the y-axis, right? Let's see if I can do this. Not bad. All right, so let's start. We're going to end up putting 4 different lines on this graph, okay? If you would like some different colors, I can pull out the colored pencils might be better for this than anything else because the space is kind of small. So you're going to need 4 different colors. If you have different colors, feel free to grab them. It'll make our picture a little easier. Sorry, I forgot to mention that at the beginning. So, yeah. We can move the colored pencils more to the middle of the class so that, you know, other people can. So. It was just a suggestion.
We can do that. I do.
We need 4 different colors, yes.
Someone the other day in history told me we're not allowed to use these sharpeners or colored pencils. Then how would you
Who told you that?
I don't remember who.
So, who's spreading these lies?
How would you sharpen your colored pencil? It'd be electric. It's the opposite.
See, the problem with the colored pencils is that does happen kind of a lot. That the inside part is broken, so you got to sharpen it, and then, you know.
They get so small.
All right. So I said we're gonna add 4 lines onto this drawing. Okay. We're gonna use kind of the whole space. So the first part, you'll see that I'm only gonna draw it kind of like half the way along the x-axis. There's a reason for that, because we're gonna take up basically the whole space. Okay, so first, let's start with probably the easiest one, okay? I want to draw a line on this chart to represent the amount of kinetic energy that the woman has, okay? So at the very first picture, we said that represents that instant when she leaves the ledge. What's her velocity? 0. So how much kinetic energy does she have? 0. And then we see as the pictures go through, right, what's happening to the amount of kinetic energy? It's increasing, right? But does the first line on my graph look like this? No. Absolutely. Right? It's curved, right? It looks like a what? It looks like a parabola, or at least half of a parabola, right? We talked about the idea that speed and energy have that quadratic relationship, right? So if we were drawing the kinetic energy here, it would look something like this.
So
Sure.
we draw that.
Draw that.
You ready?
All right. So that's the first line. Second line that I'm going to draw in blue. I'm going to draw to represent the gravitational potential energy. We saw from the picture, right, what happens to her gravitational potential energy as she's falling. It's decreasing, right? How is it decreasing compared to the kinetic energy? At the same rate, right? So in this case, our potential energy is going to start high, and it's going to go low.
Wait, where does it start?
Right? Well, you tell me. Where does it start? What does it say in the picture? Okay. Is that 10,000, right, in the picture? Okay. So, Edie, I'm not so concerned about the numbers. The shape is really more important. But you can start it up at that 10,000 line. That's fine. Okay. And it's going to decrease, but it's going to look just like a mirror image of the kinetic energy. Okay. All right. Good there so far. Say again? Yeah, the potential energy, like if we go back to, or if we go back to like this, right? The potential energy at the beginning here is 10,000, right? Okay, here's where it's going to get a little trickier, okay? And this is where our analysis of this situation goes a little above and beyond what your book takes you, okay? So I'm going to add a third line to this graph.
No way.
And I'm going to label it as elastic potential energy. It's going to be green. Okay? What would supply the elastic potential energy in this situation? The trampoline, right? But elastic potential energy only shows up if we stretch or compress something. While the woman is falling through the air, is the trampoline stretched or compressed or changed in shape in any way? No. So how much elastic potential energy is there up until this point? Zero. Okay? Good so far? All right. Up till where these lines, where I drew these lines. Okay? Because that's where the magic happens here, Edie. Okay? So that's okay. All right. Last line that I'm going to draw on this graph looks like this. That's it. I use this thing right here. That's it. Okay. No, I cheated on that one. So. All right, so the purple line here is going to represent our mechanical energy. How do we know that that represents the mechanical energy? Stays the same, right? This is graphically what conservation of mechanical energy looks like. Okay? All right, now let's deal with the difficult part of this situation. The part that happens right after the picture on your outline finishes. Okay? So, what's going to happen immediately after the picture on your outline finishes? Okay, what physically, like what's going to happen? Okay, she's going to stretch the trampoline, and then she's going to bounce back up, right? Okay, so that's what we have to deal with, right? So, let's first start with kinetic energy, because that one's the easiest one, okay? So, what does the trampoline do to her and her kinetic energy? Slows her down and eventually causes her to do what? Stop and change directions, right? So now, in relation to the graph, right, how long does it take the trampoline to stop her compared to how long it took her to fall out of the window? Is it faster or slower? The bounce happens kind of quick, right? So this red line is going to go all the way up to here, right? And then pretty steep down to there.
Doesn't go over it.
No. So Edie, let's answer that question, right? Right before she hits the trampoline, right? Is the trampoline stretched yet? No. So there's no elastic potential energy. She has reached, quote unquote, the bottom of her fall. So does she have any potential energy, gravitational? No. So all of the energy at that point has to be kinetic. Okay? All right, good there. As this kinetic energy is decreasing, what else is happening? Elastic potential energy is increasing, but here's a tricky part, right? If we call this section right here, or this height right here, 0, where does she actually go? She actually ends up going below 0. Does that make sense? Right? Because she's going to stretch out into the bottom part, right? Yes. Now, good question. Is that negative joules? Yes. But in case of joules, or in the case of joules, because it's scalar, does that necessarily mean there's a direction change? No, it just means that we got smaller. It just so happens we went below 0. We'll find when you get into like physics and stuff, where we set the 0 point is kind of arbitrary. That we can kind of put the 0 point wherever we want to, because the changes from one place to the other are all the same. Okay? So, what's going to happen to this blue line? It's going to go down, right? It's going to go under 0. And it's going to reach the bottom at the exact same time that red reaches the x-axis. Again, does it take as long? No. Does it go down as far under the x-axis as this one started above the x-axis? Right? That would mean that she bounced into the trampoline as tall as the building was. And that's not the case, right?
Yeah, I was definitely.
Okay. True. All right. Yeah, that would be good, right? All right, so now let's take the green line, right? The green line represents what? Elastic potential energy, okay? I'll draw it. Tell me if you understand why. Ready? Here we go. Oh, man.
Just a line? Straight line?
Okay. What?
Just a line.
So, okay. Then we can go. Technically, they're supposed to be curved. These happen really fast. So but more importantly, where does that green line end up in relation to the purple line? It ends up over 10,000 joules, right? Because what do we have with the blue line down here? Like a negative, right? Total has to be what? Specifically in this case, it has to be 10,000, right? So if we got a negative down here, we got to do something to account for that, right? Does that make sense? Okay. When does this happen? How far of the graph have we drawn right now? Has she started bouncing up yet? No. She is at the lowest point in the trampoline that she's ever going to be, right? At rest, kinetic energy is 0, right? Now what's going to start happening? She's going to go up. She's going to start speeding up, right? So, kinetic energy is going to do this. Trust me. Trust me. Okay. First, does kinetic energy ever go underneath the x-axis? But she's going the other direction.
Oh, you got me there.
Does that matter? No. It's a scalar quantity, right? You either have kinetic energy or you don't. Doesn't matter which way you're going, right? So that's what's going to happen to her kinetic energy, right? Potential energy, gravitational, is going to is going to come back up to this point right here. That probably should be a little more symmetrical, but I didn't draw it symmetrical, sorry. Yeah. Only to 0.
To where the red is?
Yeah, yeah, like on the x-axis, this is all the same. Okay. And what's going to happen to green? Because what green increases as the trampoline does what? Stretches. But then as she bounces back up, the trampoline isn't stretched out anymore, so green goes back down to 0. Okay? Again, that should probably be a little more symmetrical, but yep. Yes. Yes. In reality, this, yeah, it would be like a little kind of like bump. Because, does everyone understand what Jason's pointing out, right? On the trampoline, like when you leave the trampoline, it doesn't necessarily stay at the level that it was before you jumped on it. It kind of has a little bit of spring up to it, okay? So yeah, Jason, in that case, we'd probably see like a little bump here, but let's not go there just yet. That's a little bit more complex than what we want it to be. But in reality, yes, we would probably see a little increase in this, which means we might not get exactly back to the amount of kinetic energy we had when we initially hit the trampoline. That gets a little bit more difficult than we want to go right. So. All right. What point are we at right here?
Oh, we still have to come back down.
She just left the trampoline going which way? Up. What's going to happen to her kinetic energy from this point forward? It's going to decrease. Shane, what shape is it going to be? It's going to be a parabola, right? It's going to be an opposite parabola from the one that we had before. Okay?
Is it on after?
Say again? Yeah, we're going to stop it at this point. Yeah. All right. What else has to happen? Gravitational potential has to do what? Increase, right? But again, mirroring what the red one is doing, right?
It makes an out.
Huh?
Oh, it's just going to be huge.
And what about green? If it's not stretched out, if we're assuming that it's not stretched out anymore, green's just going to be right along the x-axis. Okay? There's a lot of stuff going on there, right? Yeah. So.
Mine's perfect.
More importantly, though, right? Even though the individual levels of red, blue, and green are changing, what's not changing the entire time? The total amount of mechanical is going to remain exactly the same if we talk just about gravity and just about the trampoline. Okay? Yes, it's complex. Does it make sense?
Yeah.
Okay?
It's symmetrical.
It should be symmetrical. Yes. I didn't draw it really well, especially my green line and my blue. Yeah. So it didn't draw it exactly the greatest, but it should be pretty symmetrical. Okay. All right. Good.
Look at your blue. It's off center center.
Wow.
Wow.
This is the only place that this conversation would happen would be like in honors physical science class. Like, no, it's not symmetrical enough for this. Yeah, maybe geometry class, maybe. All right, are we good with this graphical representation? Okay, let's pull out the packet that I gave you today, and let's look at some mathematical representations, okay? We are going to start on page 3 with exercise number 1. We're going to start on page 3 with exercise number 1. Well, it's page 3 of the packet. It's page 6. Is it 68? Is that what it is?
Yeah.
All right.
Anyone else have pencils that they put back in the container that's called stuff? What? It's literally called stuff management. Stuff management.
Got to manage the stuff.
Is that literally?
Top drawer. You need top drawer. The big one. There we go.
It's not labeled.
No, it's not. I need to label it.
You should label it.
Coloring devices. So. All right. Let's take a look here at a couple of exercises. So, this first one is the easiest one. I'm going to take some things a little bit deeper than I'm going to require you to do like on a quiz, but I want you to understand why we got to where we got to. Okay, so first let's start with this. A book with 67 joules of gravitational potential energy fell from a shelf and landed on the floor. What was its kinetic energy when it landed on the floor? So there's one word I want to change here. This word, when it landed on the floor. Okay? Because that implies, where is the book? On the floor. And what is it doing? Not moving. So in order to that, what would be its kinetic energy? Zero. But that's not really what this question wants you to do. Right? So we're going to change when to just before. So just before it lands on the floor. Okay? Just before it lands on the floor, what is the height of the object? Essentially, zero. If the height is essentially zero, what is the gravitational potential energy at that point? Zero. If it started with 67 joules of potential energy, and now it has zero, what happened to all that potential energy? Turned into kinetic. So how much kinetic energy should this book have right before it hits the floor? 67 joules. Okay. Now, I'm going to go through this on the first problem here. Like I said, I don't expect you to do this every single problem, but I just want to make sure that we see how it all fits together. If gravity is the only thing acting on this book, what do we know has to be true? True. From an energy standpoint, what has to be true? If gravity is the only thing acting on it, what's the title of the outline that we started yesterday? Conservation of mechanical energy. And mechanical energy is only conserved when there are only conservative forces, right? Is gravity a conservative force? Yes. So it conserves mechanical energy. Okay? Mathematically, that looks like this. Sigma MEI equals sigma MEF. Right? This was in your outline yesterday. Okay. Except I made you write the sigmas, right? Okay? And also in your outline, again, you don't have to do this every single problem. I'm doing it because this is the first problem that we do, and I want you to see where it comes from. Okay? We said that this equation can be made a little bit more detailed if we break apart mechanical energy into its individual parts. Okay? Those two equations are the same. One's just more detailed than the other one. Okay? Good? Okay. Where does elastic potential energy come from? Stretching, compressing, twisting, turning, changing shapes. Is there anything stretching, compressing, twisting, turning, changing shapes in this problem? No. Is there any elastic potential energy anywhere in this problem? Nope. So this is going to be zero, and this is going to be zero. The instant that the book leaves the shelf, the very instant that it falls off the shelf, what is its velocity? Zero. Which means, how much kinetic energy does it have at that point? Zero. So this one goes away. Just before it hits the floor, what's the height? Zero. Which means that the potential energy at that point, gravitational, is essentially zero. Okay? So now the only thing that we have left, or the only parts of this equation that we have left, are this. Do we know the initial gravitational potential energy? It was given to us in the problem, 67. And if that's what the initial gravitational potential energy is, that's what the final kinetic has to be as well. Okay? Good there? Let's make it a little bit more detailed. Exercise 2. A 0.2 kilogram object is lifted into the air and then dropped to the floor. If it is moving at a speed of 3 meters per second when it hits the floor, what was the gravitational potential energy before it was dropped? Going back to this, right, is, going back to exercise 1, is the situation in exercise number 2 any different than the situation in exercise number 1? A little bit, but are we essentially dropping something from a height, right? So energy standpoint, what happens? It starts with what? It starts with what kind of energy? Potential gravitational, and it turns into kinetic, yes? So this equation right here also applies to this problem right here. Well, let's go with that, right? So we know that, Joe, we're looking for what in this problem? We're looking for this. This is our question mark, right? We know that the potential gravitational energy that it started with is equal to the kinetic energy that it ends up with. Do we know how much kinetic energy it ends up with? Well, do we know right now? No. But we know that there are two things that affect the amount of kinetic energy something has, right? What are the two things that affect the amount of kinetic energy something has? Mass and speed, right? And what equation calculates the amount of kinetic energy? 1/2 mv squared. So we can take this equation and turn it into this equation. Which kinetic energy are we solving for in this problem? The final kinetic energy. So which velocity should we use? The final velocity, right? All right. Do we know the mass of this object? Yes. Do we know its final velocity? Yes. So we can plug those values into this equation. Right? And if I do my math correctly, I think we end up with 0.9. Okay. What unit? Joules. It's energy, right? As long as this is in kilograms and this is in meters per second, we're going to end up with joules. Okay? Good there? Okay. Exercise 4. Alfredo has a mass of 60 kilograms. He jumped off of a wall. His kinetic energy when he landed, except we don't want to go when he landed, we want to go just before he landed, was 882 joules. How high was the wall? Is this situation any different than the previous two? Yes, it's number 4. I skipped number 3 just because it's kind of the same. Is this situation any different from the previous two? It's something starting high and going low, right? So we're going to start with gravitational potential energy, and we're going to end with kinetic energy. Right? What are we trying to find here? The height. Is height anywhere in this equation? It's not. But we know that the gravitational potential energy depends on height, right? So we can go here and change this to mgh. Okay? How you do this problem from this point forward, I really don't care. Mathematically, however you solve it. I would do this first. Divide both sides by mg. And then we end up with h is equal to ke final over mg. Yes, Joe? True. Yeah, that we could have done that as well. Yep. Yep, you could have done that as well. Yep. That seems too big, Edie. So. Yeah, that seems too big. So. I think it's like 1.5. I think it's what it is. It's like one. So Alfredo seems like a daredevil, but really he jumped off of a 5-foot wall. So you know. The problems from the book that are on the calendar are similar to these problems. So you can finish up these problems if you want to, or you can do the ones from the book, as long as you get a little more practice. So. See you guys later.